Right, boys and girls, let's solve us some Schrodinger's equations today. And I've introduced it briefly and in an unsatisfactory way. I say it's philosophy plus guesswork by Schrodinger, which is historically true. And to this day we do a fairly sketchy understanding only as to why that should be the case. But we do know most of the operators that come into there, and we do know what the equation is. And unless you are diving into a black hole somewhere in the depths of cosmos, the equation is actually pretty good. As in, for light atoms up to about iron, it's actually a pretty decent description of chemistry. Beyond that, we have to go into relativity and so on. But let us go and write it down. So d by dt psi of r and t is minus I Hamiltonian, which for systems in the absence of external perturbations is just the function of the coordinate, and then acting on psi of r and t. So as I mentioned in the previous lectures, these psi's are some functions, generally complex valued, and the Hamiltonians are integral differential operators with the eigenvalues equal to the energies of the various orbitals and other types of energy levels within the system. Now, this is actually the full Schrodinger time-dependent Schrodinger equation, but the chemists have been showing a rather different equation to the second years, and will be showing to you in due course. They mysteriously claim that this is Schrodinger's equation, E psi, and in their case, for some reason, the psi does not depend on time, and the time derivative is missing. And so, what is the connection between that and this? This is called time-independent Schrodinger equation. And this is our mission today, to actually find that out. Okay, so solving EDSE. And the way we proceed to do that is exactly how we proceeded to do that in the previous lecture. We say, okay, our coordinate and time in there are the variables that psi depends on, and as per the theorem that I've shown you without proof, we can look for a solution to this equation of the following form. We will say that our psi of r and t will be a combination with some coefficients of the functions of purely just coordinates, so phi of r, and functions of purely just time. And if we manage to find the basis sets, so n and k, then perhaps with some coefficients, we will be able to find that solution. Now, for well-behaved functions, and the way functions are well-behaved, this is always true. So there exists basis sets in the functions of spatial coordinates. There exist basis sets on the space of all functions of time. You have seen a few examples already. And therefore, this must always be possible, and therefore when we are trying to solve that, we can substitute this product in as a test. That will tell us what the phi's and the g's are, and once we put them all together, we will get the general solution of Schrodinger's equation. So let's do it. So let us take that product and let us put it into the full time-dependent Schrodinger equation, and let's see what is going to happen. d by dt of phi of r then g of t will be equal to minus I Hamiltonian, that, remember, acts only on the coordinates and not the time, so I'll just skip bracket r for brevity, and then we have phi of r g of t. Okay, to any differential operator acting purely on time, functions of coordinates look like constants. We can take phi out of the phi of r d by dt g of t. Here, h is a bunch of products and derivatives with respect to just spatial coordinates, and so we can take any function of time out of the And let us do exactly the same as what we did in the previous lecture. We will divide this by the product of g and phi in order to eliminate coordinate from the left-hand side and time from the right-hand side. Or we can just divide it by g of t and then divide it by psi of r, with the result that these things will move. So that gives us, and I'll move minus I over to the left-hand side as well. So the second stage of this, if we multiply both sides by I will appear here and minus I will cancel there. So I over g of t d by dt g of t must be equal to 1 over phi and then h and phi. 1 over phi r h acting on phi of r. We arrived at exactly the same philosophy here, that is, on the left-hand side we have a function of just time, on the right-hand side we have a function of just space, and because Hamiltonian is the energy operator, so if we take the Hamiltonian, act on some function, if its eigenfunction is supposed to return the corresponding energy, then the function will be divided away, so we do expect, and this was Schrodinger's guess, that in fact this constant is the energy. That is our E, and as you will see, it will be the eigenvalue in the eigenvector eigenfunction problem. Okay, much like our diffusion equation did, what we now have is this system splits. What was previously a partial differential equation now became a system of ordinary differential equations. So if we write it with respect to time, so I'll put g over there, and I'll put I back there. Again, it will be p by dt g of t equals minus I e of t. And the second equation is that, and I will multiply it by phi, so h phi r equals e phi of r. And actually, as you can see, this now is the time-independent Schrodinger equation. Right? This is the equation that chemists told you was Schrodinger's equation. It comes out of the variable separation procedure once we have eliminated time. Now, the solutions for this you actually know. G of t is some indeterminate coefficient, let's call this a exponential minus I e t. Remember what we had in the case of the diffusion equation. When we had diffusion, this number was real. Now this number is complex. We had a minus in the case of diffusion and then time, so when we had diffusive processes, the job of the function was to decay, and this was our diffusion decay. Here, this is not a decaying thing. You know that exponential of a complex argument is a sine and a cosine, so this is actually a wave with respect to time. Part of the reason why this is called the wave equation and the function is called the wave function. So unlike the case of diffusion, this never decays, this actually continues oscillating in perpetuity all the way to the time being equal to infinity. And this equation will depend on what the content is of this Hamiltonian. It depends on what interactions we have. If we have a hydrogen atom, this will be the Coulomb interaction between the proton and the electron. If it's a bigger atom, we will have Coulomb interactions between electrons themselves. If it's a molecule, there will be further Coulomb interaction between individual nuclei and all sorts of other processes. Essentially, that depends on what the system is. But basically what this means is once we solve this somehow, what will happen, this is an eigenfunction, eigenvalue problem, we will get the corresponding eigenvalues, and the eigenfunctions are And when we assemble the actual final solution based on them, so psi of r t will be a sum over n with some undetermined coefficients that will depend on the initial conditions. These phi n's, functions of just r, times the exponentials of minus I in n t. And this is the general solution to Schrodinger's equation. We take the time-independent version, we obtain all the energies, and phi n's are called orbitals. We obtain then the time evolution part of that, we put them together, and we get the time-dependent expression. In the case of the diffusion, this was our cosines with respect to the coordinate, and that was decaying. Here we have molecular orbitals with respect to the coordinates, and then they oscillate as functions of time. The reason why this equation is so popular in chemistry is oftentimes you guys are not interested in the time evolution of whatever happens to the molecule. You are interested in its ground state. You want to know what the energy of the lowest occupied or unoccupied molecular orbital is, and to you the job really stops at the point where you have solved this equation and actually obtained the energy. Some chemists, laser spectroscopists, like to smack their molecules with lasers, and then they go into non-stationary states in which they actually evolve and things jump around. Photosynthetic reaction systems, for example. And there you need to solve the full time domain version, but for all the purposes that you have here, and that you will have an undergraduate chemistry course, you only need the orbitals and the energies, so you never see the whole story, you only see that little part of it. Okay, in that spirit, let us go and solve the time-dependent Schrodinger equation for a problem that is well familiar to you, that is the problem of particle in a box. Now, I think I've solved it when we did the ordinary differential equations. Spectroscopists must have shown it to you at some point, at least once or twice. So what we will do is I will do the time domain reading like this, but then when we go to the problems that you have already seen, I will simply write the answer for it, and then we will assemble the full-time solution. So particle in a box, you all know what it is, you even know the expressions for the corresponding eigenfunctions. We have a 0 and an A here, and again solid walls on either side, which means the wave function is 0 at the boundaries. You have things like this. That would be the ground state, just a sign. The first excited state would have a 0 crossing in the middle, like that, and you've got the expressions for the energies for them somewhere in the textbook. These, however, are the eigenfunctions of the Hamiltonian. These are the states that do not evolve anywhere. What happens if we actually perturb the system significantly out of such an eigenstate? We, for example, make it begin with a wave function that looks like this. It's called a wave packet. Then what you will see is actually in this final expression here, there will be many terms. The time dependence will start to matter, and this little pig will start bouncing around. It'll bounce off this wall, it will go to the other wall, it will bounce off, it will go. So essentially it's a particle bouncing around the well. And in order to actually see that, you need the full time dependent solution for that, not just stationary states. And this will be some linear combination of stationary states. Okay, so let us derive the equation that actually describes the time dependent behavior of the particle bouncing well. Actually, if you go to YouTube and Google the particle in a box time domain, you will see that solution sloshing around. Okay, so for that we need the energy operator. This, and I will postulate, much like I did when we did it with the quantum mechanics introduction, that some clever person has found the expression for the momentum operator in X. That's, I think it's plus I or minus I in there. It is I d by dx. don't really remember, but as you'll see, it wouldn't matter in the end. Then the energy of a moving particle is the sum of its kinetic energy and potential energy. Potential energy is Ekin plus dot. Now the potential energy is the same everywhere because the bottom of the well is flat. We can just put this to 0. But the kinetic energy, as you know, is mv squared over 2. But we need to express it in terms of momentum. And momentum is mv. So this is m squared v squared over 2m. So this is momentum squared over 2m. And then we need to substitute that expression in order to make it an energy operator. Our h, that Hamiltonian, would therefore be minus 1 over 2m d2 by dx squared. And you can see that we actually have seen this operator already in the previous lecture when we dealt with diffusion. Our time evolution part was different, it was decay rather than oscillation, but our spatial part is actually exactly the same. So we have solved that already. Okay, let us write that system of equations with this Hamiltonian in place and do a little bit of philosophy. So d by dt g of t will be minus I d of t. And then that Hamiltonian minus 1 over 2m d2 by dx squared phi of only just x equals d phi of x. It was this expression which I had solved, this equation that I had solved for you when we dealt with second order ordinary differential equations, and I'm sure a few physical chemists will do likewise. Either you already provided with solutions or somebody actually had solved that to you somewhere in physical. Okay, we know the solutions for the first one, it's all there, and this is again a bunch of sines and cosines, but before I go into them I need to rearrange it to make that obvious. We will have d2 by dx squared phi of x equals minus 2m phi of x. Remember I had lambda squared in here, and then we had sine and cosine. So it stands to reason that phi of x will be some undetermined coefficient. That was a, so let's call it b. b1 cosine root 2me plus b2 sine root 2me, and then x and x in there. And when we differentiate this twice, two instances of this root, one of them with a minus, pop out, combine, and produce minus 2me. So this is our general solution. Here we come to an interesting philosophical point. Much like we didn't know what lambda had been in the case of the diffusion until we imposed the boundary condition, we don't know what the energy is until we impose these rules. Of course, for a particle that moves in complete space without any walls, any energy is possible because momentum is essentially arbitrary. It's when we actually localize it that the quantization of the energy appears, and that is the difference between classical and quantum mechanics. When you have a classical particle moving in this well, any energy is possible depending on how quickly it moves. But when you have a quantum particle, you will now see how discrete energies come out of the boundary conditions on these differential equations. So, let us do that. We need this phi to be exactly 0 here and exactly 0 here because the particle cannot go into the wall. And the wave function must be continuous, and so it has to be 0 in the immediate vicinity of the wall as well. So we must have phi of 0 equals 0 and phi of a, which is the size of the box, also also equals 0. Well, in here, if we substitute 0 into there, the cosine, well, the sine disappears. And the cosine becomes 1, therefore P1 must be 0. So in this case, the cosine goes away. Remember when we had diffusion, we had the sine going away, but otherwise the equation was exactly the same. Okay, so the cosine term goes. From here, we conclude that our phi of x is actually v2 sine root, what was it, 2m dx. The second thing that must be true is that, and so we put a into there, v2 will cancel, so sine root 2m, and then a must be 0. And that's the consequence of this. But of course this is only 0 in the same way as we had it for diffusion, where 2m e root a is pi n, where n is an integer. When we take the square of that, 2m e a squared is pi squared n squared. Express e. And you can see there are many instances of e, so this is e-nth. And e is the familiar expression that we need to see already, pi squared n squared over 2ma squared, the famous energy level of the particle in the box. Let me see if I got all the arithmetic correct in there. Where's my energy? Pi squared n squared 2ma squared. Good. Okay, so notice the philosophy here. It's the strangest thing to happen because the fundamental quantization condition for the energy of a quantum mechanical particle came not out of Schrodinger's equation. Schrodinger's equation itself imposes no constraints on its parameters. It came out of our insistence that the box has walls. In the infinite universe, A would have been infinite, there would be a continuum of possible energies. In a finite box, as soon as we impose those conditions, the necessary requirement is that the energy spectrum of the system is discrete. So these boundary conditions naturally lead to the discretization of energies in quantum mechanics. And of course, you could argue that the size of the universe is finite, and so everything is ultimately quantized one way or another, and so there's no such thing as continuity, for example, physical energies. But these are deep philosophical and very arguable matters, because of course that implies infinite velocity is possible and so on. As soon as you make it relativistic, so even more complicated things pop out. So I'll just leave it for you to Google, but quantization conditions come the moment the system is restricted in where it can go. Right, that gives us the eigenvalues and the associated eigenfunctions. They are the signs in there. We can normalize them. You all know how to do it by now to get the famous wave functions for the energy levels. And that is root 2 over a sine, and we'll substitute those energies in, so it's pi and x over. These are the orbitals, as it were, and the energies. In our case, the source of constraints was the hard walls that we chose to impose. In the case of a molecule, the source of constraints would be the Coulomb interaction, because the electrons are tethered to the nuclei by Coulomb interactions, and they are also constrained in where they can go. As we shall see in the next lecture, that leads to the corresponding quantization conditions for the hydrogen atom. But if this were an atom, and the well was not square but Coulomb, so 1 over r, the corresponding things would have been atomic orbitals, molecular orbitals, and so on. These are just the orbitals of the simplest possible system, which is just a particle in a box. Okay, this is our phi's and our energies. As soon as we've got the energies, we know what they are in these exponents, and so we can actually assemble the general solution here. So our psi of R and t, the general solution to the time-dependent Schrodinger equation will then be a sum over k. And we have these undetermined coefficients, alpha, and I'll just absorb this little 2 over a into those alphas, alpha, k, and let's use the m index for summation, alpha m. Then the spatial part, sine I n x over a, and then the temporal part, the exponential of minus I, and then the energy I squared n squared over 2 squared t. And that is the general solution. If you have some complicated pattern at the very beginning, it will have a complicated expansion. You remember probably during your classes, I've actually made you do that. In the previous week, you demonstrated that the cosines and the sines are mutually orthogonal, so this is a complete orthogonal set of functions, and therefore a basis set. And you've also proven that exponentials, complex exponentials, are an orthogonal system of functions. So the conditions for the theorems that I gave to you in the previous lecture are actually satisfied, right? Sine is a complete basis set on the space of functions we're interested in there, and the exponential is a complete basis set on the space of functions of time, and therefore any possible function that is a solution to our problem will then be a linear combination. Let us also compare this with the things that we had for the diffusion equation. Really the only difference with the diffusion equation, wherever the final equation had been, this, and the corresponding version there, is in the case of diffusion equation, we didn't have the minus I. Right? It was real, all of it. The solutions were real, and therefore decaying. We had cosines in here and decaying exponentials in there. So the mathematics kind of comes together, right? These are both parabolic differential equations. They are both first order in time, they're both second order in space, but the difference between classical mechanics and quantum mechanics is that here we get complex numbers, and therefore instead of decay, the various functions oscillate. Okay. That was quicker than I had thought, actually. So let us go through the whole story once again from the beginning to the end, and then I'll send you off. Right. This is what chemists told you is Schrodinger's equation. That was a lie. This is what Schrodinger's equation actually is. And once you do the variable separation procedure, this comes out only as a spatial part of a larger composite problem. The way we do that is we say, okay, as per the theorem Kupra gave us in the previous lecture, any well-behaved function of R and T is a sum of products of functions of just R and functions of just T, assuming that that's a complete basis set of all functions of R, and that's a complete basis set of all functions of T, which, as we saw, they actually are when we do the math. Okay, so substituting what Germans called Ansatz into here, a substitution, much of this mechanics was done by Germans and Swiss and the Dutch, so all of them German speaking, around about 1905 to 1915, all of this. So we have inherited actually quite a lot of German terminology, eigenfunction, for example. So put it in there and do exactly the same procedure as what we did for the diffusion equation. That was to take the function of time and leave it under the derivative, and take the function of coordinate and take it out of the derivative, because the derivative does not act on functions of coordinate. Here's a Hamiltonian. Eventually it is the second derivative, but only with respect to the coordinate. So it doesn't act on functions of time, so we can take a function of time and that. Then we want to stash all time into here and all space into there. So I'll divide it by psi of r, move it over there, and I'll divide it by g of t and move it over here. The result being The time got collected on the left-hand side and space got collected on the right-hand side. The only way this can be true is if this and this are independently equal to some constant, because that's the energy operator. The constant has a physical meaning of energy. And then we have that equation, and then this equals this equation separately. So I moved g over to the other side, so d by dt g is minus iv g of t, and then this strange equation here, which actually matches to what chemists told you about time-independent one. The reason you always solved that in your second year is you are not usually interested in time dynamics, only in the energies of individual orbitals, which is what these functions are. And then you kind of assume the system always sits in the ground state and never goes anywhere. Okay, we know how to solve that, we know how to solve this. We've actually done that a few times already when you were computing eigenfunctions. And in a matrix representation, this would be a matrix and that would be a vector, and you know how matrix representations and function representations are now connected. As per that theorem, that gives us the general solution. The general psi of RT must be a sum over products. And here we had a double index summation, because in principle we want arbitrary functions here. But here we know that the two sets of functions are actually linked by the energy. So the function and the corresponding energy must match. It cannot be arbitrary, so the summation here is over just one index. Okay, the final thing to do in order to illustrate all of that is to solve a real problem for which we need to get the actual Hamiltonian. That comes out of classical physics, where we say that the energy of a particle in a box is the sum of the kinetic energy and the potential energy. Potential energy is zero because the floor of the well is flat and these walls are infinitely high, so it just sits in here and never goes anywhere else. So the potential energy is zero, and the kinetic energy is just mv squared over 2. And once we introduce momentum, that's momentum squared in the direction x divided by 2m. We open the book written by somebody clever and discover that the momentum operator in quantum mechanics is a derivative with respect to the current. So put it into here, minus I squared is minus 1. Second derivative with respect to x, 1 over 2m is there as a coefficient. So this abstract system, which was there for every possible case, becomes more concrete in that the time equation doesn't actually change, but the space equation becomes a more standard second order ODE, which we know how to solve, and we've seen many times. In particular, we've seen it this morning when we solved its rather for the diffusion. In the case of diffusion, there was a different coefficient here with different physical meaning, but it's exactly the same thing mathematically. Okay, put 2m over here, realize we have this. That's sines and cosines, and we must have root 2me in order to have this coefficient pop out. And then we have a cos term and a sine term. However, we must have the wave function 0 at the left wall, which means when we put pi of 0 equals 0, sine goes by itself, but cosine doesn't. And so that becomes 1, and so we are left with b1. Since this is 0, b1 must be 0, the cosine term goes. In the case of diffusion, it was the other terms that went, because they're physically different problems. Okay, the first wall tells us that it's just the sine, and then the second wall actually gives us a very profound philosophical statement here. Up to this point, if we didn't have a second wall, we could have gotten away with arbitrary energies. The number could have been anything. There would be no constraints. But now that we must have it 0 on the other wall as well, when we ask mathematically what that means, turns out sine has to be 0. Sine is only 0 for a few specific values of this energy. When that is equal to pi m, when we find out the corresponding energy, this is what it is. So actually the energy of things that I used, for example, in LEDs, right, the quantum dots, the irradiation spectrum of an LED lamp is the sole consequence of the electron being confined. Then it becomes quantized, then it requires a spectrum of various transitions. Okay, so that's our energy, and then only the sign survives. V2 we get from the normalization condition, that is the integral from 0 to a of the absolute square of the wave function has to be 1. You've done it in the workshop, with the result that the normalization coefficient is 2 over a. So if you do things like that, from 0 to a, phi n of x, phi k of x, if n is equal to k, you will get 1. If n is not equal to k, you will get 0. So delta n k, standard Gaussian normality condition. Once we've got that, we get the energies. As soon as we know the energies, we put them here. We know our GNs. And so that entire thing becomes possible. And the general solution to this problem is arbitrary coefficients times sines times exponentials, and arbitrary coefficients. In this case, I will not try and obtain any particular solution because mathematics gets rather messy in there. But should we have had an initial condition, for example, this yellow function here, we would have put our time to 0. We would have expanded that yellow function in this size that would have given us the coefficients. As soon as we know the coefficients, that's the complete expression for the system itself. And as you remember, then in quantum mechanics, the average observable quantity associated with any operator should have been psi of psi. So take that function, act on it with the operator, take the scalar product. That is any conceivable thing that you wanted to know about this system, because the wave function contains complete information about the system, about its future, and in fact you could run time backwards, in which case you will know the past. Any questions? Yes?
Okay, sorry for being stupid, but right on the left hand side at the bottom, we got rid of the sun sign.
Yeah?
Above.
Yeah.
Yeah.
Yeah?
Where's the sun sign go? Or do we just not care about it?
We say, okay, if the equation is true for one of them, then because it's a linear equation, it will also be true for any linear combination. So to us, if we find such phi's as satisfy this, and we find such g's as satisfy that, then any product of any pair of those two will then satisfy that. And because it's linear, then any linear combination will also satisfy that. So let's say if two functions are solutions, then their sum is also a solution for a linear equation. And so it is sufficient to take just one of these terms, find what they are, and then put them into a sum.
Okay.
All right, I'll see you at the workshops.